Hello, everyone. This is the lecture for Chapter 6. I always have to stop and point this one out, this pre-slide. The note that he has on his back, I totally understand that. It says, "Don't talk to me, I have no self-control, and will talk to you for 3 hours and achieve nothing." And then really small font, it says, "Thanks, I love you." I don't know why, but I love that. So this chapter is about statistical versus experimental control, or causality. I've integrated some things that aren't in the book about causality that I think are really useful, and they're things to keep in mind. We're going to talk about them throughout the class. So first, when you get time, you can watch this TED Talk. It's about why we are so bad at statistics. It's an interesting one. But when it comes to this topic, to better understand the world, we need to control for other explanations of an observation. There's two main ways of doing this that you'll see in science. One is experimental control, where you have random assignment and some manipulation. So you're changing something about one of the groups. The other one is statistical control, and that's using information from covariates. So when it comes to experimental control is relying on, first of all, random assignment. You need to randomly assign someone to a group. Otherwise, you really lose the power of experimental control. When it comes to random assignment, this generally implies the experimental manipulation is happening. There's some group that's being changed, intervened with. Random assignment of one participant to a single group, so they're not going to multiple groups. They're not having crossover effects. Independent assignment, so the assignment does not depend on the last person's assignment or anyone else's. And random sampling. This isn't always necessary, but random sampling plus random assignment is often the best strategy for success when it comes to experimental control. Strengths, all covariates are validly controlled even without being measured. So because we randomly assign to different groups, due to chance, both groups will be roughly the same on all covariates, measured or unmeasured. This isn't always the case. Things happen in real life, but you have your best chance when it's random. The second, you can more easily establish causality. You've probably seen this in your work. If you do an experiment, you're more likely to be able to talk about causal relationships. It also avoids the problems of statistical control, for example, selection or under or over control. We'll talk about that. Its weaknesses, though, the mechanism of causality is often unknown. How does the manipulation affect the outcome? It's often not able to be answered in an experiment. You also have problems of differential attrition. So for example, if you're recruiting people and people in the control group realize they're in the control group, often they might not be interested in participating in the study anymore. You also have issues of learning and other biases that cannot be controlled. You have difficulty in studying side effects of an experiment. So there's always other things that might be happening when you have an experimental control that are very difficult to actually account for. And then the fourth, there's often ethical or other limitations to random assignment. Things that are also very important to understand, but you can't ethically randomly assign someone to the group. So on the other hand, you have statistical control. Its strengths are that it's flexible to many different types of research designs. It works in just about any research design, actually. It can help demonstrate causality in carefully selected models. We're going to talk about how to think about this more deeply. It avoids the ethical and logistical problems of experiments. It just lets people live their life and That's often, it has more external validity than experiments, but it's very difficult to have the same internal validity as experiments. When it comes to weaknesses, you need all important covariates to be measured accurately. That's probably the biggest weakness. Any variable that might impact the outcome and might also impact your predictor needs to be measured accurately. You still have problems of differential attrition, learning, and other biases that you can't control for. There's difficulty in demonstrating directionality of the cause-effect relationship. This can be helped if there's more of a time element, a pre-post design, something like that. And there's no way to know if we included everything we should have. And that is one of the most difficult things, is you never know if you miss something. So when you're thinking about statistical control, I really like using the 4 elemental confounds to help you think about ways or variables that you should control for. The link to this in more details here. We have 4 of these. So you have the fork, the pipe, the collider, and the descendant. When it's the fork, this third variable we'll call z is actually what's causing both y and x. So x and y have a relationship because z is causing both of them. That's the fork. When you have the pipe situation, x causes z, which in turn causes y. So x has a relationship with y because it causes z, and z causes y. The collider, this one's very interesting. It's actually where x and y have a relationship because they both actually influence z. So x causes z and y causes z. And then the last one, it's similar to the pipe. It's where x causes z, z causes a and y. If we know if we have the fork or the pipe, the collider, or the descendant, this actually informs us of what we should do with this other variable, this variable z. When we have the fork, you need to condition on z. So you want to close other opportunities, essentially. So it's open unless you condition on z. In other words, we need to control for z in order to close that confound, that door of that confound. The pipe, similarly, it's open unless you condition on z. So we need to control for z in order to understand the real relationship between x and y. The collider, this one's actually already closed unless you condition on z. When you condition on z, you actually introduce a confound into the model. It's weird, but by controlling for it, you're actually adding a confound. These other 2 situations, when you control for it, you actually remove that confound. And the descendant is a lot like the pipe, where if you condition on a, it's like conditioning on z, and so it actually closes the confound if you condition on a. So sometimes we may not have z, but we might have variable a, and we can control for a, and that will be similar to controlling for z. The reason why I bring this up is this helps you have a framework for deciding, should I control for a variable or not? A lot of this is going to be based on theory or conjecture or a hypothesis. Regardless, using this framework actually helps you communicate why you control for something or didn't control for something. People can critique your decision, but at least your decision was transparent and rigorous. For example, we may have the situation where we have a fork. So let's say X is hours of exercise, Y is health, and Z, let's say, is age. So it may actually turn out that age is what causes both health and it causes how much you work out. It may not be the only cause of those things, but it causes both. So it influences how much you work out and your health. If we have that situation, then we need to control for age. In the same idea, we can think about, well, maybe we have a pipe. So we have age as the z variable. We want to understand the relationship between x and y, exercise and health. So we can think, well, the fork does make sense. Maybe age is causing both. And if so, then we need to control for it. But we also can ask, does it match the pipe? So in this situation, we'd be saying hours of exercise causes age, which then causes health. That one would be a lot harder to argue that your age is actually determined by the hours of exercise. So it's probably not the pipe. Which also means it's not the descendant, so we don't need to worry about either of those two. But what about the collider? So in this situation, we'd say that health and hours of exercise cause age. So that one, really a no deal. So we've looked through these 4 options, and the only one that really makes sense with age would be the fork. And so because of that, we would choose, we need to control for age in our model. That helps us get at the relationship between hours of exercise and health much better. I'm hoping this makes sense. We're going to go over this in class more. When we have covariates, we're going to bring this up. So the fork, the pipe, the collider, and the descendant are the 4 elemental confounds. There are 4 ways that a variable a confound, an extra variable, can influence the relationship between 2 things. One thing to keep in mind is that you can have a combination of these things in some way. So for one variable, it might be the fork, but then with another variable you have, it might be a collider. So you need to think through these for each one, for each predictor of interest. All right, so it turns out experimental and statistical control are not mutually exclusive. You actually can do both. What's cool is when used in tandem, it actually helps us in a lot of ways. We can supplement random assignment and experimental control with statistical control. In that case, it increases precision and power. So our estimates are more precise and we're more likely to correctly reject a false null hypothesis. We also have the issue of when you use random assignment, there's a chance that there's going to be differences between groups. We can use a control variable to try to control for any chance differences between the groups. And last one on here, we can quantify and assess indirect effects, which is also called mediation. We're going to talk about that in a later chapter, in chapter 15. The first one, increases precision and power, can help if you consider the example from the book where they have data on PTSD, post-test, pre-test, therapy, and gain. We want to know if there was a difference between the 2 therapies. So you can see there's therapy 1 and therapy 0. There are 3 main ways that we could analyze this data right here. A t-test. If we do a t-test, we see a p-value of 0.12. The difference between the means is -3. Simple regression, you actually get the same thing. There's a difference of -3, same p-value. But when you control for pretest, it doesn't change the difference between the therapies, but now it's significant. Because we pulled out some noise, that's in the data due to where somebody started. When we control for the pretest, all of a sudden we are able to account for why people are at different levels, and we can see the difference in the therapy much more clearly. Same estimate, different p-value. You can see this, the box plots show how these two tests are comparing them. There's a lot of overlap. So the red and purple overlap quite a bit, so it doesn't really look like there's much of a difference. But when we account for pretest, now we see that there's really no overlap when you consider the two lines. They are totally separate, and so we should see a difference there. And that's because we're able to see the pretest scores. Over here, we ignore the pretest scores. By accounting for this additional variable that was important, we actually can see the full separation that there really is. There's also this invulnerability to chance differences between groups. It helps us when we randomly assign. Sometimes there are differences between the groups just by chance. We can statistically control for variables where we see differences, and that can help the random assignment. It can actually help it so that the groups are more alike. And then the last one we'll talk about a lot more is the idea of mediation. We actually can look at, does our experimental manipulation affect one variable that in turn affects another? This is a really cool analysis. It has additional assumptions that are a little bit tougher, but it can answer a really good question. It's how is our experimental control affecting our outcome? Is it through this one? And you'll see this in like psychology, where you have an experiment where you give an intervention, and then the outcome, they report higher life satisfaction, or they report better relationship status. But often the question is, so how did that happen? And often the mediator will be something like self-efficacy or better understanding of communication. And that helps us understand how our experiment affected our outcome. A few final thoughts. Here's some takeaways from this quick lecture. First, even in experiments, measure covariates so we can use statistical control with it. It also helps us understand if our groups are different in some way. 2, experiments are not the only way to demonstrate causality. It's tougher, but still possible. If you control for all the right things, all the forks, and all the pipes, and all the descendants, and don't control for any colliders, you can have a causal model. Still difficult, and often not well received yet. But it still gets you a lot closer than if you are just saying, well, we control for a bunch of these things. Third thing, use linear models to assess both experimental and non-experimental data for more precision. Takeaway is regression can be used for experiment and non-experimental data. And there's ways that we can make all of those situations better by carefully thinking about things that we should control for. And again, a beautiful picture from Glacier.